We are literally building digital brains. And no, that's not science fiction anymore. It's a technology called deep learning, and it is already completely reshaping our world. So in this explainer, we're going to break down exactly how it all works. The entire field of AI, everything you hear about, really boils down to one incredibly powerful question. What if a computer could learn, not from a rigid set of instructions, but from experience? What if it could just look at data and see patterns, make predictions, in a way that feels, well, almost human? That's the core idea we're going to unpack together. All right, so here's our game plan. First, we'll nail down what deep learning actually is. Then, we'll peek under the hood to see the surprisingly simple way these digital brains learn. After that, we'll meet the specialist brains, different types of AI for different jobs, see how they're already all around you, and finally, we'll take a look at what the future holds for this incredible tech. Okay, let's dive right into section 1. What is deep learning? This is all about a massive shift in thinking, moving away from just programming a computer to actually letting it learn on its own. So at its heart, deep learning uses something called artificial neural networks, which, as you might guess, are inspired by our own brains. Now the deep part, don't let that intimidate you. It just means these networks have lots and lots of layers. Just imagine, the first layer might spot simple things in a photo, like an edge or a color. The next layer puts those together to see a shape, like an eye or a nose. And the layer after that combines those shapes to recognize a face. It's this beautiful hierarchy of understanding, going from super simple to incredibly complex. And here's the real game changer. With older methods, a human programmer had to literally spoon-feed the important features to the computer. You'd have to say, okay, a car has 4 wheels, it has windows, it has a certain shape. With deep learning, you just show it millions of pictures of cars, and it figures out what makes a car all by itself. That right there is its superpower. Especially when you're dealing with messy, unstructured stuff like images, audio, and all the text on the internet. Okay, so how on earth does a digital brain actually learn? Well, it's not magic. It's actually a pretty simple and really elegant loop. It makes a guess, it checks how wrong it was, and then it makes a tiny correction. That's it. Over and over and over again. So let's walk through it. First, you show the network an image, let's say a picture of a cat. All that pixel data flows forward through the layers, and at the very end, it makes a guess. Dog. Okay, not great. Next, it calculates its error, basically a number that says how wrong it was. But here's the secret sauce. That error signal gets sent backwards through the entire network. This is called backpropagation, and it tells every single connection in that brain how much it contributed to the mistake. Finally, the network takes that feedback and adjusts all those connections, just a tiny bit, to be a little less wrong the next time around. Now, one tiny adjustment doesn't sound like much, right? But the magic is in the repetition. This loop of guess, check, correct happens millions, sometimes billions of times. With every single cycle, the network gets just a little bit smarter, a little more accurate, until eventually it can spot that cat almost every single time. All right, on to section 3. Let's talk about architectures, or as I like to call them, the specialist brains. Because, just like our brains have a special area for vision and another for language, deep learning isn't a one-size-fits-all solution. You need different tools for different jobs. You've basically got 3 main specialists on the team. First, you have CNNs. Think of them as the vision experts. They are masters of understanding pixels and images. Then you have RNNs, the storytellers. They're built for anything that comes in a sequence, like speech or text over time. And then you have transformers. These are the current rock stars of the AI world, the power behind things you've definitely heard of, like ChatGPT. So what makes transformers so incredibly powerful? It's a really clever innovation called the self-attention mechanism. See, instead of reading a sentence one word at a time, a transformer looks at the whole thing at once. And for every single word, it asks, which other words in this sentence are the most important for understanding me? This is how it knows that in the phrase, an apple fell, apple is related to fell. But in an Apple phone, Apple is related to phone. It's all about understanding relationships and context, and it's a total game changer. Now, even within the transformer family, there are 2 major flavors. Think of them as 2 sides of the same coin. On one side, you have models like BERT, which are designed to understand language. They're like detectives, reading text forwards and backwards to get the deepest possible context. They're amazing for things like figuring out if a movie review is positive or negative. On the other side, you have models like GPT, which are designed to generate language. They are absolute masters at predicting the next word in a sentence, which is what allows them to write essays, answer your questions, and create entirely new text from scratch. Which brings us to section 4, deep learning in your world. Because let's be clear, this stuff isn't just theory or happening in some far-off research lab. You might not even realize it, but this technology is already woven into the fabric of your daily life. And it is mind-blowingly fast. Just to give you a sense of the speed we're talking about, a popular vision model called YOLO, which stands for the great name You Only Look Once, it can spot and label objects in a live video at up to 155 frames per second. To put that in perspective, that is way faster than our own eyes can even process. It's happening in true real time. So where is this power showing up? Well, every single time you unlock your phone with your face, that's a CNN at work. When you translate an entire web page with a single click, or talk to Siri or Alexa, that's a transformer understanding and generating language. It's even powering absolutely critical advances, from helping scientists discover life-saving drugs to helping doctors spot cancer in X-rays with superhuman accuracy. It's everywhere. So that brings us to our final section. We've seen what it is, how it works, and where it is today. So now for the really exciting part. What's next? Where are these digital brains headed? Well, in the very near future, the big push is for smaller, leaner AI that can live right on your phone instead of in a massive data center. Looking a bit further down the road, we're talking about entirely new kinds of computer chips, neuromorphic chips, that are literally built to function like a human brain, which could make them 1,000 times more energy efficient. And then, way out on the horizon, you have quantum AI, which could use the bizarre rules of quantum physics to solve problems that are completely impossible for us today. But with all this incredible power comes some huge responsibilities. These models are only as good as the data we train them on. And if that data has human biases in it, the AI will learn and even amplify those biases. And here's the other tricky part. These systems can be a black box. They're so complex, even the people who build them don't always know why they make a specific decision. So what do you do when it makes a mistake? That's why this new field called explainable AI, or XAI, is becoming so crucial. It's all about cracking open that black box so we can understand, trust, and ultimately be responsible for what these digital brains are doing. And that really leaves us with the ultimate question. It's one thing to build a digital brain that can learn how to do things. It is another thing entirely to guide what it learns. As these incredibly powerful minds continue to evolve, the central challenge for all of us is this. How do we make sure they learn to reflect not our flaws and our biases, but our absolute best values?